If you remember in the last lecture, I said that stoichiometry I knew was your favorite subject. Well, today we're going to cover your next favorite subject, and that is limiting reactants. So we're going to go to calculations involving limiting reactants, but I know that this is difficult for some of you, so let me just give you a real quick example of something very simple that has a limiting reactant. Let's say you want to go to the show, you have $5 in cash, you have a vehicle full of gas, and the ticket for the show is 10 bucks. What is your limiting reactant to be able to complete what you want to do, which is to go to the show? Well, do you have enough gas in the car, and do you have a vehicle? Yes, plenty of that. Do you have enough cash to pay for the ticket? No. So your limiting reactant in this example is the fact that you don't have enough money to pay for your ticket. That seems really, really simple. Just keep that process in mind as we get ready to go through these examples. Don't get caught up in all the numbers and all the writing. Just focus on the purpose, what a limiting reactant is, and it should make a little bit more sense. Let's take a look at what a stoichiometric mixture is. A stoichiometric mixture contains the relative amounts of reactants that matches the numbers in the balanced equation. So in our example, we take nitrogen gas and add it to hydrogen gas to make ammonia gas. So in this example, and you'll notice in the balanced reaction, it takes 1 nitrogen molecule for every 3 hydrogen molecules, and your yield will be 2 ammonia molecules. So before the reaction, you notice that we have the right number of each reactant in order to group them to make them into 2 ammonia molecules. So we have 1 nitrogen molecule, 3 hydrogen molecules, the same thing in each red circle, and when you put those together, you come up with 2 ammonia molecules after the reaction. And they have all been used up. Both of the reactants have been used up to produce the maximum amount of product. Let's look at a limiting reactant mixture. So here's our balanced reaction that we just dealt with. In this case, we're looking at what happens before, what we're dealing with before the reaction. So we group them together just like the others. So we have 1 nitrogen molecule for every 3 hydrogen molecules, and we group those off, and we know that for every 1 nitrogen and 3 hydrogen, we get 2 ammonia molecules. But notice when we group them up, just like you used to do in elementary school when you would put the groupings together, we end up with 2 nitrogen molecules left over. So we have these ammonia molecules made, but we don't have any hydrogen to react with those nitrogen. So the question is then, what is our limiting reactant in this case? What limited our ability to make the maximum amount of ammonia molecules? And the answer to that would be hydrogen. If I had 6 more hydrogen, I could make more ammonia molecules, but I can't because I don't have enough hydrogen. So I did not have enough hydrogen. It is limiting. That means that nitrogen gas is in excess. Since you've had some experience before with limiting reactants, I think the best thing to do is to get into a couple of examples. So we'll have 2 examples and 1 question that has multiple choice answers. And I'm going to suggest that you maybe watch the first one thoroughly and then start the second one, pause it, try to finish it yourself, and then watch the tutorial and do the same thing with the last one. Okay, with this reaction, what we're going to do is look at it and realize, first of all, that we have to have a balanced reaction every single time. And this one is not balanced. So let's just do a really quick balancing. This is something you've already mastered, so we're not going to go back through and hash through that so that we have a balanced reaction. Now let's look at the problem. For the following reaction, suppose exactly 5 grams of each reactant is taken. So I'm going to take time just to write that down right here so I know exactly what I'm dealing with. So I have 5 grams of each reactant. Determine which reactant is limiting and what the mass of the excess reagent will remain, or what mass will remain after the limiting reactant is consumed. We know that we can go grams to moles, mole to mole ratio, moles to grams, and that we always have to focus on this mole to mole ratio. We cannot compare grams to grams because their masses are not the same as in compound form. So the first thing we need to do is change our grams to moles. Okay, so I've paused it and I've taken time to go ahead and do the math to show you that we change grams to moles, and I did that by calculating the mass of NaCl, the molar mass of H2SO4, and converting grams of each one to moles. And just for the sake of room and needing some more room, what I'm going to do is I'm going to go ahead and change these numbers over and put them right here below the reactant, and get rid of some of this so that we can have room to do the next step. I suggest on your paper that you allow enough room to be able to show all of your work, but that's not always the easiest thing when it comes to doing this on the computer. So these numbers have come from doing the conversions, and this is what we did in the last lesson and something that you're very familiar with. Now at this stage in the game, I don't expect you to show me where you wrote out and calculated the molar mass of your reactants, but the conversion that we had up here showing taking 5 grams to moles, that must be shown on your work. So we've taken grams to moles. Our next step is to do a mole to mole ratio. And we're going to compare the two reactants because it says that it wants to know which reactant is limiting first of all. So I'm going to take, just like you did in the stoichiometric examples, I'm going to write down the two things that I'm comparing. And I'm going to take the top number from the balanced reaction, just like we did in the last video. And I'm going to always choose the first reactant in the equation to do my reasoning with. So I solve for x, so 0.0856 divided by 2 equals, and let me clear this up a little bit, this is a little messy. It is a 2, not a 0.2. So x equals 0.0428 moles of H2SO4. Now is the reasoning. So I look at this, and by putting this information up here, what I'm saying is, if I use all of my sodium chloride, which is the 0.0856 moles, how much H2SO4 will I need? So this is how much I would need. I would need 0.0428 moles. So I compare it to how much I have, which is up here. And that's when I ask myself the question, do I have enough? I need 0.0428. I have 0.051. So my answer is yes, I have enough. So this H2SO4 is not what is going to limit me. What's going to limit me is the NaCl. So my limiting reactant is sodium chloride. This step you do not have to do. I'm just going to show you that whether I started with the NaCl or the H2SO4, I'm going to get the same limiting reactant either way. So let's say I want to use all of my H2SO4. So I use 0.051 moles of H2SO4. Use it all up. How much NaCl would I need? So I do my cross multiply and solve for x. So 0.051 times 2. 0.102 moles of NaCl would be what I needed. Up here, this is how much I have. And I ask myself the question, do I have enough? I need 0.1, I have 0.08, my answer is no. And if I say no, I don't have enough, then this is what limits me. And this check just backs up the fact that the first reaction that we did, showing that we had excess H2SO4, meant that the sodium chloride was limiting, and we back it up by showing this second example. This second one is not necessary, but I just wanted to give you that information, maybe to clarify how we did it and why we did it. Okay, now that we've established which one is the limiting reactant, let's look back at the problem and remind ourselves what they actually are asking. It says to determine the limiting reactant, so I always put the LR above the limiting reactant. That shows that you know which one it is. And what it wants to know is how much of the excess reagent, which is the H2SO4, will remain after the limiting reactant is consumed. Okay, so what we have to do is we have to look at it and say, I'm going to use up all of my NaCl. And this goes back to our first ratio that we looked at. And what I'm saying is if I use up all of it, how much of the H2SO4, that certainly does not look like H2SO4 there, do I need? So if I use up all my NaCl, I'm going to need 0.0428 moles of H2SO4. That's how much H2SO4 is going to be used up in the reaction. And I'm going to have leftover H2SO4. So if I'm going to use all of that, and this is how much I start with, all I need to do to find out how much is in excess is to subtract what I use out of it. So if I take 0.0510 and subtract 0.0428, I come up with 0.0082 moles left over. And it says, let's see, it wants the mass of the excess reagent left over. So all I have to do is then take 0.0082 moles and change it to grams. If you remember from the beginning of the problem, when we did the molar mass, we said that H2SO4 weighs 98 grams per mole. So I'm going to take 0.0082 moles times 98 grams over 1 mole and change that back into grams. And that will come out to be 0.8036 grams of H2SO4 left over. For example number 2, I'm going to go through it a lot quicker with a lot of stopping and seeing the new information put in just because of time. So you need to make sure that you pay attention to what I'm doing, and when you need to pause it and work on it yourself. So let's look at the problem. It says for the following reaction, suppose 10 grams of each reactant is taken, calculate the limiting reactant and the theoretical yield in grams of each product. So I have 10 grams of each reactant, and before I go any further, I have to make sure I have a balanced reaction. So I'm going to balance this reaction real quick. And the first thing I need to do is to remember that I need to change grams to moles and look at a mole to mole ratio. So I'm going to change grams to moles. All right, so I have changed these to moles by using the molecular mass. So the next step that I need to do is to do a mole to mole ratio and say if I have 4 moles of aluminum, how many moles of chlorine do I need to react with it? So it's 4 to 3 from the balanced reaction. If I use up all of my aluminum, I'll be using up 0.371 moles. How many moles of chlorine am I going to need to react with that much aluminum is our next question. When I do the calculations, I find that I would need 0.2783 moles of chlorine gas. And I look up here, this is how much we have, is 0.41 moles. I need 0.27, I have 0.14. The question I have to ask myself is, do I have enough? The answer is no. Since I don't have enough chlorine to react all of my aluminum, chlorine is what becomes my limiting reactant. So the next thing I need to do is go back up to our problem. It wants to know the theoretical yield in grams of each product. And in this case, we only have 1 product. You may have some problems where they have 2 or 3 products, and you have to calculate this for each one. So once we do the mole to mole ratio and we find out that we would make 0.094 moles of aluminum chloride, we take its molecular mass and we find out that theoretically we should come up with 12.53 grams of aluminum chloride. So the last exercise that you need to do on your own and see if you can come up with the correct answer is this one. It talks about the reaction we started with limiting reactants, and follow through, see if you can come up with the right answer, and if not, let me know in class and we'll go over it together.